Let us look at this polynomial in variable x. The highest degree of this variable is 3, hence it is a cubic polynomial. Now note that the coefficient of x cube has to be non-zero, or a has to be non-zero. Why? If a was 0, then the term with x cube would vanish and the highest degree of this polynomial would become 2. It would be a quadratic polynomial then. Hence a has to be non-zero for this polynomial to be cubic. Now let us look at a linear polynomial with degree 1. If we were to put 2x plus 3 equals 0, we would get x equals minus 3 by 2 or minus 1.5. Now for this value of x, the value of this polynomial is 0. Hence, minus 3 by 2 is a 0 of the polynomial 2x plus 3. Graphically, we would get a straight line. We can take two values for x, find out the corresponding value of y and draw this straight line. Now note that x equals minus 1.5 is where this line intersects the x-axis and the value of y is 0. So the 0 of this polynomial is the intersection point on the x-axis. Let us look at another polynomial. It is intersecting the x-axis at 2 points, also known as zeros of this polynomial. Note that the degree of this polynomial is also 2. Let's look at another. If we count the number of intersection points with the x-axis, we see there are 3 zeros. Note that the degree of this polynomial is also 3. Isn't it interesting? The number of zeros is equal to the degree of the given polynomial. Now let us look at this graph. We see that it is intersecting the x-axis at just 1 point, whereas the degree of the polynomial is 3. So this means that degree tells us the maximum number of zeros a polynomial is going to have. So this polynomial has 1 zero, but its degree tells us that it could have at most 3 zeros, not more than 3. Now let us look at a problem. For the given graphs of y equals px, find the number of zeros in each case. So let us look at the first graph. Let us see the intersection of the graph with the x-axis. There is just 1 point, so it has 1 zero. Let us look at the second graph. Let's count the points of intersection on the x-axis. There are 4, hence 4 zeros. For 4 points on the x-axis, the value of this polynomial is 0. Let us look at the third graph. If we check the points of intersection, there are 2 points on the x-axis for which the value of the polynomial is 0. Hence, it has 2 zeros. Now let us recall the linear polynomial we saw before. We saw that minus 3 by 2 was a 0 for the polynomial. Now instead of 2x plus 3, let us generalize it and write it as ax plus b. We find that minus b by a is a 0 of the polynomial ax plus b. So see that there is some relation between 0 of the polynomial and the coefficients. Now let us take a polynomial of a higher degree, a quadratic with degree 2. Can we find the zeros of this polynomial? Yes, we could split the middle term. Let us simplify and put the polynomial equals 0. So we get 1 and 3 as the zeros of this polynomial. Now let us look at the sum of these zeros. Wow! It is equal to the negative of coefficient of x divided by coefficient of x square. Let us look at the product of these zeros. Wow, that is equal to the constant term divided by the coefficient of x square. Let us make this easier. Let us write the polynomial as ax square plus bx plus c, and let us call its zeros as alpha and beta. So we see that alpha plus beta is equal to minus b by a, and alpha times beta is equal to c by a. There is another way to look at this result. Since alpha and beta are the zeros, we could write the polynomial as k times x minus alpha times x minus beta. Let us simplify and compare like terms on both sides. Upon cross multiplying, we arrive at the same result. Alpha plus beta is equal to minus b by a, and alpha times beta is equal to c by a. So for a quadratic polynomial with degree 2, there can be at most two zeros. Let us call them alpha and beta. So we see that alpha plus beta is equal to minus of b by a, and alpha times beta is equal to c by a. Now what if it was a higher degree polynomial? What if it was a cubic polynomial? Now since the degree is 3, it can have 3 zeros at most. Let us call them alpha, beta and gamma, and follow the pattern. So the sum of zeros would be equal to the negative of b by a. What do you think c by a is going to be? It would be alpha beta plus beta gamma plus gamma alpha, or sum of product of its zeros taken two at a time. What do you think d by a is going to be? It is going to have a negative sign and will be equal to alpha times beta times gamma. Note that the negative sign appears with alternating coefficients. So b has a negative sign, c has a positive sign, and d has a negative sign. Let us look at a few problems. Find zeros of x square minus 2x minus 8 and verify the relationship between its zeros and coefficients. How shall we find the zeros? Splitting of the middle term. So the factors of 8 could be 4 and 2. But 8 has a negative sign. So let us put a negative sign with one of them. So minus 4 and 2. Does it satisfy the middle term? Yes, it does. Minus 4 plus 2 gives us minus 2. Now let us split the middle term and simplify. Now in order to find the zeros, we have to put the polynomial equal to 0. So we get minus 2 and 4 as the zeros of the polynomial. Now recall the relationship between zeros and coefficients. Yes. Now sum of zeros should be equal to minus b by a. Yes, it is. Similarly, product of zeros ought to be equal to c by a. Yes, it is. And we have verified the relationship. Now let us look at another problem. Find a cubic polynomial with the sum of the product of its zeros taken two at a time, and the product of its zeros as 2, minus 7 and minus 14 respectively. So let us break the statement into three smaller statements. Now since it's a cubic polynomial, which means degree 3, so there shall be at most 3 zeros. So sum of zeros, product of zeros taken two at a time, and product of zeros. Now recall the relationship between the zeros of a cubic polynomial and its coefficients. So we could write 2 equals minus b by a, minus 7 equals c by a, and minus 14 equals minus d by a. Now there are two unknowns in each of these equations. So let us assume a value for a. Let us take the simplest. Let's call a as 1. That gives us values for b, c and d. Now we can substitute the values of these coefficients in the polynomial. We could have taken any other value for a. But remember that a has to be non-zero. Only then the polynomial would be cubic.